Welcome. In this lecture, we're going to talk about Newton's laws, forces, and math. This comes from chapter 3, 3-1 through 3-4. We're going to talk about classical mechanics, Newton's first law, force, math, and Newton's second law. I know it sounds like a lot, but it shouldn't be too bad. First of all, let's talk about the goal of classical mechanics. So, if we know the initial conditions like position and velocity and the physical properties like mass and volume of an object, and if we know or can measure the interactions that the object has with its environment, classical mechanics asks, can we predict the subsequent motion of the object, or can we find the position and velocity at all future times? So in classical mechanics, we start out with what is called the particle model. In order to understand the effect of the interactions between an object and its environment, we start by simplifying the object by thinking of them as particles. This is called the particle model, and it just means we can ignore the internal structures and motion and assume that all parts of the object move the same way. So this is useful for learning fundamentals, and then eventually we will analyze extended objects. And this tau is a physics joke. It's a spherical tau, since we treat objects as particles, hence spherical tau. This specific one comes from SPS, which is the Society of Physics Students. So let's talk about these interactions between objects and their environments. First, we have an apple. It falls from a tree. The environment is the earth, and the force acting on the apple is gravitational. Then we have a car that comes to a stop. The relevant environment is the road, and the force is frictional. Finally, we have a compass needle, and the needle points north. The relevant environment is the earth, but this time the force is magnetic. As you see from the table, we describe the interaction of an object with its environment in terms of force. But what is force? Forces are a push or a pull on an object in a specific direction. Force is also a vector. Like I said, there's lots of vectors in this class. And in one-dimensional motion, the direction is just given as negative or positive. So we have our origin position, and this we can establish and decide. Generally, we would pick the starting point as the origin, but I mean, some situations arise otherwise. So anyway, we have the origin, and then we say that motion to the right is positive, or forces to the right are positive, and forces to the left are negative. Newton's first law of motion says, consider a body on which no net force acts. If the body is at rest, it will remain at rest. If the body is moving with constant velocity, it will continue to do so. So, right at the beginning of that, it mentioned the idea of net force. Let's talk about what that is. So, net force is just the vector sum of forces acting on an object. So we show vectors acting on an object here. One of them points to the left, so we would say that's negative, and one of them points to the right, so we would say that's positive. And these are vectors, so the magnitude of the arrow represents the magnitude of the vector. So it looks like these forces are equal in magnitude, but opposite in direction. So when we find the net force, we sum them up, but because F1 is negative and F2 is positive, they end up with a net force of 0. Let's have a momentary diversion to talk about reference frames. Every observer has their own reference frame. So long as they have a coordinate system and are able to measure position, velocity, and acceleration. An example here, you are riding in a car. Someone is riding in a bike next to the car, and someone else is standing on the sidewalk watching both of you. All three of you have your own reference frame from which you can observe your environment and take measurements. If the net force on a body is 0, then it is possible to find a set of reference frames where the body has no acceleration. A reference frame where an object has no acceleration is an inertial reference frame. Newton's first law is also called the law of inertia. That's why we have inertial reference frames. So if no net force is acting, no acceleration, it is an inertial reference frame. Okay, now let's think about applying the same force to objects of different sizes. Let's say you're trying to push a car with a certain force, and then you try to push a bike with the same force. The bike and the car are going to react differently to the force. This should be something that you have some intuition with. The car might barely flinch or not move at all, while the bike will start rolling along. The objects experience the same force, but have different acceleration. This is due to their different masses. Mass is the property of an object that resists change in motion. A car obviously has a lot more mass than a bicycle, so it takes a larger force to get it moving. Mass is a fundamental part of an object that doesn't depend on the force applied. So we're applying the same force to both of these objects, but if we applied a bigger or a smaller force, it would do nothing to change the mass. It would just affect the acceleration of the car. Also, mass is a scalar quantity, and I think we mentioned this last week, that a scalar doesn't have a direction, it just has a magnitude. But force is a vector, not a scalar. That brings us to Newton's second law. Newton's second law says that the vector sum of the forces acting on an object is equal to the mass of the object times the acceleration of the object. This is true for the vector components as well. So we can split because force is a vector, we can split the net force. Pause real quick and say the sum of the forces is the same thing as the net force, just so we're clear. Anyway, the net force can be split into the different directions because, again, it is a vector. And so we end up with just the mass times the acceleration in that direction, equaling the sum of forces. So let's do some dimensional analysis to understand the units here. So mass times acceleration has units of mass times length times time to the -2 or divided by time squared. That also means force has those same units, since force equals mass times acceleration. So force has units of mass times length times time to the -2 or divided by time squared. These units are called newtons or newtons. So 1 newton is 1 kilogram meter per second squared. I'm going to give you a tip here. It's totally fine if this if it doesn't stick with you right now. But when we are building up our units, like when we go from the basic SI units to other units, if you have trouble remembering what 1 newton is, for example, go back to Newton's second law, force equals mass times acceleration. This is what I do. If I'm trying to make sure my units cancel out properly and I can't remember what a newton is, I go back to this fundamental equation and I'm like, okay, mass is in kilograms, acceleration is meters per second squared, 1 newton is a kilogram meter per second squared. Okay, let's talk through this sample problem to see how to solve force problems. So the question says, a worker, W, pushes a loaded sled whose mass, M, is 240 kilograms for a distance d of 2.3 meters over the surface of a frozen lake. The sled moves with negligible friction on the ice. Negligible here just means you can ignore it. So we can ignore friction. The worker exerts a constant horizontal force F of 130 newtons as she does so. If the sled starts from rest, what is its final velocity? So, the first thing to do when solving force problems is to select a reasonable inertial reference frame and pick the coordinate axes, which means to find, well, in one dimension anyway, it means to find the positive and negative directions. So, our reference frame is just going to be an observer standing near the sled who isn't moving. And an example of a bad choice of reference frame would be the frame of the sled. Since the sled is likely experiencing acceleration, that wouldn't be an inertial reference frame. Next up is our coordinate axes. So we'll just set the origin to be where the sled starts. So our origin, initial position here. This means that if we're writing our knowns and unknowns, we can say the initial x position is 0. And then positive again is to the right and negative is to the left. The next step is to draw what is called a free body diagram. A free body diagram shows the forces acting on an object. It shows not just the forces, the magnitude and direction of each force acting on an object. So that's what's here at the bottom. You simplify it down. This is where that particle model comes into play. You simplify your object down to a dot and put it at the origin of a coordinate system. And then you draw the forces acting on it. In our case, there's only one force that we're paying attention to anyway, and it's the force on the sled by the worker. And that is pointing to the right. That's the other part of this too, is we want to label each force with 2 subscripts. So the first subscript is whatever the object is. So the force on the sled, and then the second subscript is what is applying the force. So the force on the sled from the worker, FSW. Then we find the vector sum of the forces acting on the object. So in our case here, it's just the force on the sled by the worker. And from Newton's second law, we know that the sum of forces is equal to the mass times the acceleration. That's what we just learned a few slides ago. So we can set these 2 equations equal to each other. And we find that the force on the sled by the worker is equal to the mass of the sled times its acceleration. So now we can solve for acceleration and by dividing mass on both sides. So we end up with acceleration is the force on the sled from the worker or by the worker divided by the mass of the sled. We were given this force, it's 130 newtons. We were also given the mass, which is 240 kilograms. Means we can plug those in and calculate our acceleration is 0.54 meters per second squared. Then we can combine forces with kinematics to find the velocity of the sled after it travels 2.3 meters. We'll use this kinematics equation since it is the only one without time and we weren't given time. And let's go through really quickly and just make sure we have everything we need for this. So we want to find the final velocity. We know the initial velocity is just 0. We're starting at 0. Then plus 2 times the acceleration we just found, and the displacement is given here. So, oh yeah, I just said this, but the velocity initially is 0 meters per second. The acceleration 0.54 meters per second squared. The displacement is the final position minus the initial position. The initial position is 0. We decided, because that's the easiest thing to do, is to set your initial position to be 0. So that tells us that the x displacement is 2.3 meters. So we can then plug those things into our equation. We don't have to do any rearranging at first anyway, because we're solving for the final velocity, and that's what is solved for here. So initial velocity is 0, then we have 2 times the acceleration times the displacement, and this gives us 2.484 meters per second, whole thing squared, but that is the final velocity squared. We want just the final velocity, so we have to take the square root now. And that gives us 1.576, or we'll round to 1.6 meters per second. Okay, so now we're going to walk through, well, we're not just going to walk through, we're going to do another example. So this one says a crate whose mass M is 360 kilograms rests on the bed of a truck that is moving at a speed of 105 kilometers an hour. The driver applies the brakes and slows to a speed of 62 kilometers an hour in 17 seconds. What force, assumed constant, acts on the crate during this time? Assume that the crate does not slide on the truck bed. Okay, we're going to start out with our knowns. Oh, and here's a picture of the truck with the crate. So, what do we know? We know the mass of the crate is 360 kilograms. We know the initial velocity of the crate and the truck is 105 kilometers per hour. We know the final velocity is 62 kilometers per hour. And we know the time interval is 17 seconds. What are our unknowns? I made that an M. No. So we don't know the force on the crate by the truck, and we also don't know the acceleration. So let's go through those steps again. First step was the reference frame. Reference frame. So we are going to choose a frame that is at rest with respect to the truck. At rest with respect to, that's what that stands for, the truck. And we will also do our coordinates. This is going to be positive x direction. This one's negative x. And this is our origin, which is also what we will say is the initial position, like right before the truck starts to brake. And then just reminder that it's moving in the positive x direction. Next up, we have our free body diagram, which can be written like this, FBD, just so that I don't have to write out 3 full words. I'm also going to do the third step here too, which is labeling. So our free body diagram, we will again just draw a coordinate axis, positive x, negative x, and then let's think about this. So our initial velocity is to the right, but we're braking. So the acceleration needs to be in the opposite direction of the velocity. So that means that acceleration needs to point to the left. And force and acceleration are in the same direction. So the force also needs to be to the left. So here is our dot that represents the crate, and then our force. Force on the crate from the truck. It's a vector. Okay, then we do the vector sum of forces. Vector sum of forces. So the only forces we have are in the x direction. So sum of forces is in x. And then I'm going to teach you something that, or am I? Yes, I will. One thing that we want to do when writing our sum of forces equations is we want to just plug the sign in this equation so that we don't forget. So the force we have is in the negative x direction, so it's going to have a negative sign there. Okay, and then we also know that as this is the sum of forces, it is equal to the mass of the crate times the acceleration. So the question asked us for the force, but obviously we need to find the acceleration first. So we can use the kinematics equations for this. But we don't have any information about displacement, or I mean, we have the initial position because we could say it was 0. But other than that, we don't have any of those. So that really narrows us down to just one kinematics equation. Oops, that's the eraser. So final velocity equals initial velocity plus the acceleration times the time interval. So let's check. We have the final and initial velocity. We don't have the acceleration, and we have the time interval. So perfect, only one thing we don't know. So let's rearrange this and solve for acceleration. That means we're going to subtract the initial on both sides and divide by the time interval. That is our equation for acceleration, but we're going to need to do some conversions first. Because if we go back up here, we have velocity in kilometers per hour and time in seconds. And one other thing to think about, the units of force are kilograms times meters per second squared. So we want to keep things in seconds or convert them to seconds. So even though that means converting two variables, like both of the velocities instead of just the time, it makes sense so that we can use the units of newtons in the end. So let's do this conversion. Let me walk you through how. So 105 kilometers per hour for the initial velocity. So we want to get this in meters and in seconds. So let's do meters first. There's 1,000 meters in 1 kilometer. And I put it like this because kilometers are on the top here. So I need to put it on the bottom there so that they cancel. Then now we can do this all in one go. So the next thing to convert would be from hours to minutes. So 1 hour is 60 minutes. So now I put it on the top because hours are on the bottom here, and I need those to cancel. And finally, going from minutes to seconds. So 1 minute is 60 seconds. So let's look at our units. So we have kilometers here and here, so those cancel. We have hours there and there, so those cancel, but then that leaves us with meters per minute, but we can cancel out the minutes. So that leaves us with the units of meters per second. And this is 29.7 meters per second for the initial velocity. And the final velocity, we do the exact same thing. 62 is the value though. Kilometers per hour, and then we just are converting the same way. So 1,000 meters per 1 kilometer. 1 hour is 60 minutes, and 1 minute is 60 seconds. And this gives us 17.2 meters per second for the final velocity. So now that we have those converted, we can do the acceleration. So the equation for that again was the final velocity minus the initial over the time interval. Final velocity just found 29.7 meters per second minus, sorry, that's the initial velocity. Final velocity is 17.2 meters per second minus 29.7 meters per second divided by 17 seconds. And this gives us an acceleration of negative 0.73 meters per second squared. So now, we can find the force. Let's see, force. So we know that the force on the crate from the truck is equal to the mass of the crate times the acceleration. The mass is 360 kilograms, right? Yes. 360 kilograms times the acceleration of negative 0.73 meters per second squared. And this gives us a force of negative 264 newtons. So there is one thing that I said that I want to point out and correct your thinking on, because I just realized that it's important. So if we go back here to this sum of forces equation, I said that we need to plug in the negative sign here for the force, but we also need to do that for the acceleration. So because we know that the acceleration is in the same direction as this only force that we have, we need to also include its negative sign. So you're not always going to know the direction of the acceleration, because sometimes you have a bunch of forces acting and you don't know for sure. But in that case, you will just end up with, like, if you guess the wrong thing, you'll just end up with a negative instead of a positive when you're doing the math, but we'll get to that. Anyway, so that is why right here, I did not include that negative sign here, because technically they're both negative signs, those cancel, so that when we plug in our negative acceleration, we can show that we have a negative force. So apologies if that was confusing, but I wanted to point that out now because that is something we will continue to emphasize with forces. Okay, that's everything. I hope you have a great day.